Yo guys, what's up? Today we're back with another video, and today we're going to be talking about U-Substitution, or essentially another integration technique to add to your toolbox. I think this is learned at the end of Calc AB slash, the start of Calc BC, and it's definitely before you learn about integration by parts or by fraction decomposition. So U-Substitution is pretty simple. All you're doing is you're taking a function that looks pretty hard to integrate, but using certain tricks and tools, you're able to integrate the function very, very easy. And so essentially what you're doing with U-Substitution is you substitute the variable or the function with something else, such as U. That's why we call it U-Substitution. Really, you can replace it with anything, but you'll see later on of why we call it U-Substitution. So in order for it to be more clear, I'm going to go through the first example. So our first example is going to be to integrate the function 2x minus 1 to the third power with respect to x. And so you might be wondering that we could just expand the function, so we can see. But in order to do that, you have to do 2x minus 1, 2x minus 1, and then 2x minus 1. And then you have to find this, and then you have to find that. And it's really difficult to expand the function and then integrate everything to C. However, with U-Substitution, it's very, very easy to do this. So essentially what you're going to do is you're going to call a variable U. We have a U, right? And we're going to say that U is equal to 2x minus 1. The reason why is because U-Substitution is right here. We want to make this the U. And from here, we want to make du equal to 2 dx. The reason why it's called du is because we're taking the derivative of u, or in this case, 2x minus 1, and then du will be 2 dx. And so essentially how I see U-Substitution is that when you get du, and then you get 2 dx, you can basically isolate the dx in order to just get dx by itself. So du over 2, or 1/2 times du is equal to dx. So essentially, since you have u is equal to 2x minus 1, and then your 1/2 du is equal to dx, you essentially have everything for a perfect U-Substitution integration. So from here, 2x minus 1 just becomes u to the power 3. dx equals 1/2 du, or du over 2, so you can just replace it with du over 2. Remember your technique for integration. You can just take out the 1/2. So this whole integral becomes u to the third du. And from here, you can just do 1/2 times 1/4 u to the fourth plus c. Now, we're not done yet, because for a successful integration, you want to plug in the original function. So from here, since we have 1/2 times 1/4, we can just do 1/8. We plug in u again to be 2x minus 1 to the fourth plus c. This is our integral. And if you don't believe me that it works, then let me show you. In order to take the derivative of this function, we have to do chain rule. So we do 1/8 times 4, 2x minus 1, and then it goes down to the third power. And then you bring the chain rule, so you just multiply this by 2, because that's chain rule, times 2. 4 times 2 is 8. 1 over 8 times 8 is 1. Therefore, the derivative of this function is equal to 2x minus 1 to the third. So chain rule works. U-Substitution works. So it works. Trust me on this one. On our second example, this one's kind of difficult, but it's really basic as well. We have the integral of x squared times 3x to the third minus 1 to the third power with respect to x. So essentially for this one, you're going to do the same thing, but it might be a little bit difficult to see why U-Substitution might be available, but trust me on this one. We see that the inside of the function that's being carried to the power 3 has a degree that's higher than x squared. That means that if we were to take u to be 3x to the third minus 1, then we can make du equal to 9x squared dx. And then from here, we can isolate dx and make du over 9x squared equal to dx. So from here, you might be wondering that it might not work or that something might happen, but trust me on this one, it works. We have x squared. We replace the function inside the being carried to the power of 3 with u to the third du over 9x squared. Since everything is being multiplied, we can cancel out the x squared, and we just left with 1 over 9, so we can just bring that outside. And from here, we just do normal integration, such as 1 over 9 times 1 over 4, u to the 4 plus c. And we get 1 over 36. Replace the function back again, 3x to the third minus 1 to the 4 plus c. And essentially, it works out again because when you do chain rule, you get 1 over 36 times 4, 3x to the third minus 1 to the third, times chain rule, so it'll be 9x squared when you take the derivative of the inside function. And then when you have everything sorted out, you'll just get x squared, 3x to the third minus 1 to the third. So again, U-substitution works. It's just an easier method to integrate functions that look impossible, but in reality, it's just like a little cool trick to keep in mind, whether you're doing college calculus or whether you're in AB or BC and you're taking the AP exam. So our third example is a very interesting one. So it might not look like you can use U-substitution, however you can. And here's what I mean. You have the integral of tangent x dx. And you might be wondering to yourself that there's literally no other way to integrate this other than if you're advanced already. But if you're advanced already, you would already know this. But for my people out there that haven't learned U-substitution, you're able to do this, but you have to go back to your trigonometry toolbox. Here's what I mean. We know that tangent x is just a subset of functions, and we know that tangent x is equal to sine of x over cosine of x. And then from here, we can actually just replace it with sine x over cosine x with respect to x. And then from here, you want to be very careful to what you're making your variable. You want to make it simple, but you also want to have a way to cancel out the function, if you know what I mean. We know that in order to isolate du, we have to have something under du, like dividing it, And here's what I mean. Let's say we make u equal to sine x, and then du equal to cosine x dx. Theoretically, it could work because you have u, which is now sine x, so u over cosine x, and then du is cosine x. dx is du over cosine x, I'm sorry. And then from here, you get u over cosine square x du. If you're advanced enough, I think you're able to integrate this and still get the same answer. However, I'm not that advanced in mathematics, and so I cannot tell you what that integral is, which is why you should be very careful when choosing u. Now, can you brute force it and find what's u? Yes, but I think it's just better to think about it and then to just, to think about it and then see what you need to do. That's logical. So in this case, u is going to be cosine x. And then our du, remember, is going to be negative sine x dx. From here, we divide by negative sine x to isolate dx. And then we get sine x over cosine x, which is now u, negative du over sine x. Now, this cancels out, and it leaves us with negative 1 over u du And you can take the negative out or you can keep it in. It doesn't really matter. From there, we integrate. And then we have negative natural log absolute value of u plus c. Now, since we know u is cosine x, we just replace it back into the function. And that's our answer. Whereas you can take it one step further and simplify, because really it's natural log secant x plus c. But I'm not going to do all that because this is acceptable as well. Essentially, the reason why is if you go back to your logarithmic rules, you can, for a natural log, you can bring over the power here and essentially make it natural log cosine x to the negative first power plus c, and essentially you get natural log secant x. Because when you do that, you get 1 over cosine x, which is equal to secant x. So just a fun little simplification. The last integral I'm going to do is it's one I've already done on this channel, and one that's already very, very famous. Well, not famous. I mean, it's not famous, but you know, my calculus teacher did it, so now it's time for me to pass it on. So we're gonna do a U-substitution with bounds, and here's what I mean. So let's say we had the integral from 0 to 1 of x e to the x squared with respect to x. Now, essentially, we're not going to do plus c because of the definite integral, obviously. But, you know, just don't forget that, please. Like, don't put plus c on any definite integrals, please. You might be wondering why this might be a special, you know, integral. The reason why it is because when you do U-substitution on here, you have to change the bounds. And here's what I mean. So there's two ways to solve this problem and you get the same answer. And should I do both of them? No, I'll do both of them. So essentially, we want to find u. We know that x is a lower degree than x squared, and we know that e to the x squared is an impossible integral to integrate if you just left it by itself. However, since we have the x in front, we're able to see that intuitively we can make u equal to x squared, and then du equal to 2x dx. So essentially from here we keep 0 to 1 of x e to the u du over 2x. And it cancels out. So we bring the 1/2 in front, 0 to 1 of e to the u du. Now, I'm solving this the long way. So this is the long way, and here's what I mean. This is kind of complicated, and this is why I don't want you doing this if you do it. I'm taking off the bounds for now. The reason is because since this is the long way, I will be showing you why. We have 1/2 e to the u du, right? And then from here we integrate, we just get 1/2 e to the u. We don't do a plus c, but instead we just put in back the function of u. So we do 1/2 e to the x squared as our answer, right? And then from here we take our bounds from 0 to 1. And from here we get that the answer is 1/2 e minus 1/2. And you can simplify further to get 1/2 times e minus 1 is your answer. This is called the long way because you didn't change the bounds within the system. You waited until you integrated and then put the u back in, and then you took the bounds. But there's an easier way, and here it is. Take that same integral, same u, same everything. But instead, what we want to do is we want to put our bounds within u. And here's what I mean. Essentially, how to change bounds, you want to take u of 0, or u of 1 in this case, and get 1. Since u is equal to x squared, when you take u of 1, you're putting in 1 into the function of x squared. So you're doing 1 squared equal to 1, right? And then U of 0 is just going to be 0 if you're doing this intuitively. The reason why we want to do this is because it's going to end up the same answer when we essentially put back U, but it's just saving us the time and effort from solving it the long way and just knowing our bounds already for U. Essentially, you're going off to a different universe when you change U, because when you go to the U universe, you're not in the X universe no more. So you have to change the bounds. However, for this problem, we can see that the bounds will stay the same. However, it's good to be in the habit of changing your bounds for U substitution. It will help you a lot. And here's why it helps a lot. So essentially, we get the same thing. We get 1/2 e from the bounds of 0 to 1, because remember, they stay the same. However, it's always important to check. E to the u du. And essentially, we just do 1/2 e to the u from 0 to 1. And this is why it's important, because instead of having to put in u for the x and then having to integrate with x, you can just put in the bounds for u. And it's that simple. And you literally get the same thing. And this is why it's very important. Let me see. Am I able to make one on the spot? Okay, so I'm not able to make a question up on the spot. However, it works. Just trust me on this one. Always change your bounds when you're using U-substitution in case you do have any bounds in the integral. But essentially, this is U-substitution. It's just an easier way to do your integrals. And if it look impossible, then you might want to use U-substitution and keep that in your toolbox. And it looks very simple right now. However, like, it's very, very important when you're taking your AP test or your college test. If it gets very, very important. So this has been U-Substitution. Thank you for watching. If you've enjoyed, please like the video, subscribe. That's U-Substitution. Pretty simple, pretty simple. I'll see you in the next one, and goodbye.